Hello, my name is Nesrine Abbas. I will present you a summary of the results in the paper titled Linear Algorithms for Red-Blue Domination in Convex Bipartite Graphs. I will start the presentation with the problem formulation, followed by some motivation that will help put the problem in context. The graph family that is the focus of the paper will be introduced for those who are unfamiliar with it. We will see the status of the problem in existing literature, then present the algorithms that were developed in the paper, and conclude the presentation. Given a bipartite graph, G, with partitions x, y, and edge set E, and an integer k, is there a subset of x of cardinality at most k that dominates all vertices of y? We call this problem red dominating set problem. A red dominating set in a bipartite graph is equivalent to a set cover, where each set is represented by a vertex in X, vertices of Y represent elements of the universe, and an edge exists between a vertex in X and a vertex in Y if the corresponding set contains the corresponding element. The set cover problem is to identify the smallest collection of subsets whose union equals the universe. The decision version of set cover is one of the known anti-complete problems. The term red dominating set is better suited and is what has been used in the literature for graph contexts. The name originates from the view of a graph as partitioned into red and blue sets. By definition, the red dominating set in a bipartite graph will be independent. We can define the problem in general graphs. In this case, the red dominating set may be connected. In the connected red-blue dominating set problem, we are given a graph G whose vertex set is partitioned into parts red and blue, and we are asked to find a connected subgraph induced by a subset S of red such that each blue vertex of G is adjacent to some vertex in S. The problem has been studied for general graphs in Abbas et al., where the authors develop an exact exponential time algorithm for connected red dominating set. The problem appears in a number of applications. As mentioned in Abbas et al., red-blue dominating set can effectively replace the more general dominating set in a large number of network protocols. For example, to find a subset of select servers that covers all hosts, and select here can mean powerful hosts or hosts not in sleep mode. And they mention that this makes dominating set-based routing more efficient. Focusing on bipartite graphs, we can find a few applications. For example, suppose you have an exam bank of questions for a course and associate a concept to each question. You would then like to create an exam with k questions such that the questions in the exam cover all concepts. In the problem is studied using real data to find a subset of stations that covers all trains. In the graph, an edge exists between stations and trains if the station is part of the train path. In Dekel and Sani, a scheduling problem is formulated on bipartite graphs. They consider the problem of scheduling a set J of n unit jobs to minimize the number of tardy jobs, and each job has a release time and a due time. Each vertex in partition X of the bipartite graph corresponds to a job, and each job is adjacent to vertices in Y in the time range of between their release and due time. And they seek a subset of the jobs that can be scheduled on one machine in such a way that no job is scheduled before its release time or after its due time. Even though in this reference, the problem studied is a scheduling problem, but the graph built is a convex bipartite graph because the time range for each job consists of consecutive vertices. A red dominating set in such a graph is a subset of the jobs that covers the whole time range. And convex bipartite graphs are the graphs that we consider in this paper. A bipartite graph G with vertex partitions X and Y and edge set E is said to be Y-convex if vertices of Y can be ordered so that for each X in partition X, neighbors of X appear consecutively in Y. I will simply refer to that graph as convex bipartite. Such an ordering is called convex ordering and can be computed in linear time. The graph in the figure is convex bipartite. Given the restrictive nature of the neighborhoods of four vertices in X, we can represent the convex bipartite graph by just storing for each vertex X the first vertex of Y and the last vertex of Y in its neighborhood. We call those vertices left and right of X. For example, in the graph shown, left of X3 is Y2 and its right is Y7. We will represent the graph by what we call the neighborhood array N. The neighborhood array N has an entry for each vertex in X, and each entry stores the two values left and right. We assume an additional ordering of the vertices of X besides the convex ordering of the vertices of Y. This ordering is called Lex convex ordering, and it has been used in other papers such as the paper by Pend and Pradhan. In that ordering, xi comes before xj in the ordering if left of xi is smaller than left of xj, or the two lefts are equal, but right of xi is smaller than right of xj. And ties can be broken arbitrarily without disrupting the ordering of other vertices. Such an ordering can be obtained in order in big O n plus m, where n is the number of vertices in the graph and m is the number of edges. In the motivation, we have seen that convex bipartite graphs arise in real-life applications. We see now where they fall in the bipartite graph family, then we will see the status of red-blue domination in this family of graphs. We're considering only graphs that are finite, connected, undirected, with no loops and no parallel edges. Bipartite graphs are those whose vertices can be partitioned into two independent sets. A complete bipartite graph has all possible edges between the two partitions. Informally speaking, perfect elimination bipartite graphs are those bipartite graphs that have a perfect elimination scheme for the edges, such that the neighbors of each edge in the current graph induce a complete bipartite graph, and there are no edges at the end. A chordal bipartite graph has no cycle on more than 4 vertices. Chordal bipartite graphs are a subset of perfect elimination bipartite graphs, and convex bipartite graphs are a subset of chordal bipartite graphs. The problem is NP-hard on bipartite graphs by virtue of it being a set cover. In 5, this author shows that the problem is NP-hard for perfect elimination bipartite graphs. In 2016, Golovac et al. Developed an enumeration algorithm for the problem on chordal bipartite graphs. And it runs in order n times the minimum of m log n and n squared delay time. Therefore, the first output appears after that much delay. An algorithm to enumerate red dominating sets in convex bipartite graphs is presented in 5, and the first output of that algorithm appears after order n plus n time. Unlike chordal bipartite graphs, convex bipartite graphs are not symmetric. An algorithm for red domination on convex bipartite graphs might not work for blue enumeration. In this paper, we present 2 algorithms for convex bipartite graphs, one for calculating a minimum cardinality red dominating set, and the other for calculating a minimum cardinality blue dominating set. Though the results in 5 can be used to calculate a minimum cardinality red dominating set, the algorithm we present here is simpler and slightly faster. Let's first consider calculating a minimum cardinality red dominating set, i.e. a subset of X that dominates all vertices in Y. The graph shown is a convex bipartite graph. The vertices filled in red are a minimum cardinality red dominating set for that graph, which I abbreviate as MCRD set. It consists of vertices x2, x4, and x7. There are some simple observations that will help us obtain an MCRD set for G. If G is an MCRD set, then the X vertices in the set cannot have neighborhood containment. Otherwise, G is not minimal. For example, X1 and X2 cannot be in the same MCRD set. The second observation is that neighborhoods of two consecutive X's in the dominating set are consecutive in Y. Otherwise, some vertices in Y are not dominated. For example, neighborhoods of X2 and X4 and neighborhoods of X4 and X7 are consecutive, but neighborhoods of X1 and X4 are not. The third observation is that for each X in the dominating set, there can be at most one other X in the same dominating set that satisfies the above point about neighborhoods being consecutive. For example, we can have an MCRD set that contains X2 and X4, as shown in the figure, and there is another MCRD set that contains X2, X3, and X7, but we cannot have an MCRD set that contains X2 and both X3 and X4, because it wouldn't be minimum. Those observations are summarized in this slide. The implication of those observations is that we can ignore vertices of X whose neighborhood is contained in another when calculating an MCRD set. If we remove such vertices from the graph, we obtain what we call a maximal proper subgraph. An MCRD set in a maximal proper subgraph is an MCRD set in the original graph. In a maximal proper subgraph, the first vertex is always in the MCRD set G. We will start with this vertex in our algorithm, and suppose we have a partial set D. We find the first vertex of Y that is not dominated. From among the neighbors of Y, of that vertex of Y, we select the vertex in its neighborhood that has the most right reach, meaning the vertex that has the largest right. In a maximal proper subgraph, from among neighbors of vertex Y, the vertex X with the most right reach is the one with the largest index. We calculate the maximal proper subgraph and calculate the neighbor of Y with the most right reach for each Y in two pre-processing stages. Both stages can be done in time linear in the number of vertices in the graph. After those two steps, the algorithm is simple. Start with an empty dominating set D. Go sequentially through vertices of Y, starting from Y1. Add to D the neighbor of the current vertex Y with the most right reach. Once we have gone through all vertices of Y, all vertices of Y will now be dominated by vertices in D. Given the neighborhood array N that represents the graph, those steps can be done in time linear in the number of vertices in the graph. Because convex bipartite graphs are not symmetric, the algorithm for MCRD, or minimum cardinality red dominating set, will not work for a minimum cardinality blue dominating set, abbreviated as MCBD. Let's consider calculating a minimum cardinality blue dominating set, i.e. a subset of Y that dominates all vertices in X. The graph shown is a convex bipartite graph. The vertices filled in blue are an MCBD set for the graph. It consists of vertices Y2, Y6, Y8, and Y11. We notice in this set that its vertices are in the neighborhoods of vertices of X that are not in a maximal proper subgraph, as defined earlier in the slides. For example, Y2 is in the neighborhood of X1. and y6 is in the neighborhood of x5, y8 is in the neighborhood of x6, y11 is in the neighborhood of x9, all of those x vertices would not be in a maximal proper subgraph. In fact, we find that we need those x vertices whose neighborhoods are a proper subset of other neighborhoods to find an MCBD set. Another observation we can make is that each of those vertices is the right of those x's. For example, y2 is the right of x1, yc the right of x5, y8 is the right of x6, and y11 is the right of x9. This leads to the following two properties that we used to develop the algorithm. We call a set that has those two properties a proper MCBD set, proper minimum cardinality blue dominating set. Those two properties say that we can choose the innermost right in an MCBD set, and we can traverse vertices of X sequentially. We apply this result in the algorithm that computes a proper MCBD set for convex bipartite graphs in linear time. The algorithm starts with an empty set D and with current being x1 and next current plus 1. We will keep going while there are undominated vertices in X. We will update next by looping through vertices in X sequentially to skip those dominated by right of current and whose neighborhood set is not contained in the neighborhood set of current. After this initial loop, next is not in the neighborhood set of current. We loop once again to find the vertex with the innermost right. So loop through remaining vertices in X to update current so that it is the largest index vertex that has the innermost right. If we have reached an X that is not dominated by right of current or the end of the graph, then we add right of current to D and increment current and its next, and keep going until we reach the end of the graph. We have shown that both minimum cardinality red dominating set and minimum cardinality blue dominating set are solvable in time linear in the number of vertices for convex bipartite graphs. The most expensive step is the initial step to build the neighborhood array to represent the graph, and this needs order n plus m, where n is the number of vertices and m is the number of edges. The results for MCRD have been used for an enumeration algorithm in a previous paper, but it's not clear if the results for MCBD lead easily to an enumeration algorithm because the results that we have apply to a particular blue dominating set, not to all blue dominating sets. As well, there's a big gap between the costs for MCRD for Corder bipartite graphs and those for convex bipartite graphs. So it leaves an open question if this gap can be narrowed if there is a faster algorithm for MCRD for Corder bipartite graphs. And this concludes the paper. Thank you for listening.